Hello, geometry folks. Today we're going to be talking about segment lengths in circles and all of the theorems that revolve around that. So what you're going to need today are your notes. I printed out for you a little cheat sheet chart, as well as you're going to need your notebook because we will be writing some stuff down. And then if you so desire, you can have a calculator and then a pen or pencil. With that, we'll get started. So we're talking about three specific theorems, which ultimately boil down all to the same theorem, and this is the cheat sheet for them. So this sheet will reference back after we've talked through this theorem, so that way when you go back to your notes, it's something easy to reference and easy to remember to help you study for the test. So with that in mind, the first theorem, or the first part of the theorem, is segments of chords. Remember that chords are pieces or line segments that are within a circle. So when chords intersect both in the circle, the chords break into segments that are equal when multiplied. So what we mean by that is this piece times this piece of that chord is equal to this piece times this piece of that chord. So AX, that piece times XB is equal to CX times XD. So let's see this in action, if you will. So we have, oh, this is weird. I would have labeled the center K and then the segment X, but that's okay. So we have 9 times X, that piece, times X, so this piece times this piece, is equal to this piece times this piece, which is 40. 10 times 4 is 40. Now we're going to divide both sides by 9, and we get X is equal to 49ths, which can't be reduced, but if you want to write that as a decimal, that would be 4.4 repeating. If you want to write it as a decimal, I would have left it as a fraction. But that's the first example. The second part of this theorem is segments of secants circle theorem, or when the segments are now secant lines or secant segments. So when two secants, remember that a secant is a line or a line segment that intersects the circle at 2 points on the circumference or on the outside. So when two secants intersect a circle, the segments of the secants, the chord, and the whole secant are equal when multiplied together. So what we mean by that is from M to O, that portion is the secant segment, and then from, let me use purple for this, the chord is N to O. So we're saying that when we take the whole line times the external part, so actually MN is the external part in our little equation here, times the whole line, which is MO, is equal to the external part here, MP, times the whole line segment, which is MQ. So let's see that in action with an example. So we want the external part times the whole segment equal to the external part times the whole segment. So MN is 8 times MO is X is equal to MP, which is 6, times MQ, which is 16. So we're taking 6 plus 10. Hope everybody followed me on that. 6 times 16 is a 96. We have 8x equal to that 96. Divide both sides by 8, and we will get x is equal to 12. And that is the second part of the theorem. And the last part of the theorem is, what if that secant line, so if we would have had, let's say, a line from here to here, that would have been like the last example where we had a chord and an external part. But now if we moved this line so that it's a tangent line or only touching the circle once, that's going to change my formula slightly. So if this would have been C and then we moved it, that's what we're trying to say, to a tangent line. That means that our equation would be the external part, df, times the whole line, which is GD, and then our other line, the external part, which is CD, and the whole line, if it stops at C, is also CD. So our theorem or our formula would be df, that segment, times GD is equal to CD squared. And let's look at an example so that we can make sense of this. So this example, we have df to be x, so df is x times gd is 25 plus x is equal to cd, which is 30 times 30 or 30 squared. So x times 25 is 25x, x times x is x squared, and 30 squared is 900. So now when we see that we have an x squared in here, we're going to have to set one side equal to 0. So what I do is I keep my x squared term positive, and so I move everything in this case to my left side. So we have x squared plus 25x. I want to write this in standard form. Whoa, vocab back from Algebra 1. Weird. Okay, anyway, so when we have an x squared term and an x term and a c term, that means that we're going to have to factor, and everybody loves factoring. So we need to think of two numbers that multiply to negative 900, which is kind of crazy. So factors of 900 that add or subtract to 25. So those two numbers are 20 and 45. Those two numbers multiply to 900, but we need one of them to be negative, and we want the sum of those two numbers to stay positive. So I'm going to make my 20 negative and my 45 positive equal to 0. So when I set these two equal to 0, I'm going to start the next part up here. I set my first factor, x minus 20 equal to 0, giving me x is equal to a positive 20. And then my second factor, x plus 45 equal to 0. If I subtract, that's going to give me a negative distance right here. So my only answer, I mean, technically we have two answers from our factors, but my only answer that makes sense in the context of this picture is x is equal to 20, which should be my answer. And for my last example, we're going to do this one again. We have the external piece, 12, times the whole piece, which is d to g. That's going to be x plus 12 is equal to 24 squared. So 24 squared is 576. And then 12 times x is 12x, and then 12 times 12 is 144. So we subtract 144 from both sides, leaving us with 12x equal to 576 minus 144 is 432. And if we take 432 divided by 12, we should get an answer of x is equal to 36. Okay, so now looking back at this little cheat sheet or foldable that you've glued into your notes. So when it says what makes the segments and what do I do, when we have this image like this where we have two chords or two segments within the circle, we take the piece times the piece, which is equal to this piece times that piece. And then if we have two secants or two lines that have a chord inside and are connected or intersecting on the outside, then we take the external piece times the whole piece equal to the external piece times the whole piece. And then our last example or type of problem with this theorem is if we have a secant and a tangent line. So that would be the external piece times the whole piece, and then the external piece times itself, or squared. So hopefully this little cheat sheet will make sense now that we've gone through every single part of this theorem and also for examples with this theorem. So I want to thank you for taking good notes, and I shall see you soon.